So now we're going to look at applying the first derivative or the second derivative law for different optimization problems. For majority of these optimization problems, you're looking at the first derivative because you're trying to find a minimum or a maximum. You've seen minimum and maximum problems when we talked about quadratics, but now we're going to be looking at different types of functions and how we can take the derivative to help us find those minimum and maximums. There's a three-step approach in order to do this, and it's just like any word problem. First, you want to determine what is relevant to the problem, create the model, and assign your variables. The second part is restating the problem based on what's referred to as an objective function. It takes everything that you know about what's happening in this problem and putting it in terms of one variable. Then you optimize. In order to optimize, we take the first derivative and find the maximum or the minimum value. So let's look at an example. For this particular problem, we're trying to find the shortest distance between the line y equals 2x minus 1 and a point negative 3 and 4. So if we actually put negative 3 and 4 on our graph, we have a point here. And our line goes through negative 1 and it has a slope of 2, so something to that effect. We're trying to find the closest point that exists on this line here. So ultimately, we can kind of infer that it's going to have to be the 90-degree point. At 90 degrees, it is the shortest distance, but we know it also relates to a right-angled triangle and getting closer and closer. So we're looking for the minimum distance. As we get closer to this distance here, which is at the 90 degrees, that will be the closest point away from negative 3 and 4. So intuitively we can see what we're working with, but we need to figure out what this coordinate point is. That's our goal. So we've created a diagram to kind of idea what's going on. We do need to define our variables. Now we also know the distance formula. We want to have a minimum distance. So if we use the distance formula, that will help us figure out what it could be. And distance formula is based on Pythagoras, so if you haven't memorized the distance formula, it's just setting up a Pythagorean theorem to figure out then we want to get a minimum of our distance. That's our goal. And we want it in terms of our coordinate points. Now, right now this is our overarching idea. We want to take a minimization of the distance, and we want to be able to figure out the coordinate pair that's going to minimize that. We want to restate the problem now in an objective function, which means that we want it in terms of one variable. So we're going to use the other information that we know to ultimately narrow down our equation. So we know a couple of things that we can fill in. One of them is that we know a point. So if we fill in negative 3 for our x2, either order doesn't really matter, and we put in 4 for our y2, that at least is now put in one point in there. The other thing that we know is that the point lies on this line. Now it's set up so I actually know that y is equal to 2x minus 1, so I can actually have a point here that's going to be some x value comma 2x minus 1. That's technically what this point is represented by. So I can now plug that into my equation to replace x1 and y1. So the distance that we know so far is negative 3 minus x all squared plus 4 minus, in this case, 2x minus 1, so 2x plus 1 if you don't have brackets, all squared, which then can simplify down to your distance formula, square root of negative 3 minus x all squared plus 5 minus 2x all squared. Now we can work with this a little more, distribute, combine like terms, and simplify down our function. And you should get to this point here. So now we have our objective function that we need to work with. From this point here, we now have to actually find the minimum or the maximum. In this case, we're looking for a minimum. We want to get the shortest distance. So in order to do that, we have to now take the derivative. So if we take the derivative of the distance, we're going to have to use our chain rule, we have an overarching function of a square root. So 1 over 2 with the square root of the entire thing inside there still, minus 26x plus 5x squared, multiplied by the derivative of what's inside, which in this case is negative 26 plus 10x. Working with this derivative, we also want to find the min-max now, so we actually have to find the zeros. So if we have 10x minus 26, and that's our numerator, and 2 times our square root of 34 minus 26x plus 5x squared, what will actually make this equal to 0? Well, if you look at your numerator, if you have 10x minus 26 is equal to 0, xn is going to equal 13 over 5. The denominator will help us with our non-permissibles, the top will give us our zeros. So that's going to be our x value for finding the minimum. But of course in this problem we want to find the coordinate point. So we have to also find your y value. And y we can find by using our 2x minus 1 equation and plugging x in. When you plug that in, you're going to find you're going to get 21 over 5 for your y value. So on the line y equals 2x minus 1, we have a coordinate point at 13 over 5, 21 over 5, that will give us the minimum distance to the point negative 3 and 4. So the main thing you want to keep in mind when you're working on the applied optimization problems is that ultimately you want to get down to one equation, an objective function, that you can then take the derivative of to find the minimum or the maximum. So the best thing to do is practice setting up your equations and make sure they make sense. Draw a good diagram so all your variables are defined.